Hello, welcome. So I thought I'd do a quick video on something I've been looking at just today. So one of the problems, so in my race quad series, I was out flying actually my friend was flying it the other day, and we had a radio failsafe. And it was a little way away, not that far. I shouldn't have radio failsafe, but I thought I'd investigate a bit more. Anyway, when I was out flying it yesterday, I had multiple failsafes with it only a few meters, 20 meters away from me. So I figured that something was wrong, and it wasn't the radio range. And I had a little clue because I've had issues with failsafes before, particularly on ELRS, but occasionally on CRSF, to do with CPU load. And so my first suspicion was that this was CPU load related, and I dug into that a bit. And but this video is about how do you find out what your CPU load looks like. So it's a bit of a developer topic here, but hopefully it'll be useful. So you can see my console here. And I'm going to start up mavproxy, and if you don't know how to use mavproxy, I suggest you search on the wikis, good instructions there. So I'm going to start up mavproxy, and I'm going to connect it to my race quad here. So you can see, and I might just switch my transmitter on just to give the full effect. So pause while I switch my transmitter on. Right, so you can hear my transmitter going there in the background. So, okay, and we're going to get various error messages coming out of this. But, so what is the way of telling whether you've got CPU load issues or not? Well, the first thing, obviously there's the PM log message, and you can look at the PM log message, and that gives you a view of the overall load for the main thread. But that's a pretty granular, coarse-grained picture, and what I want is something a little more detailed. So the first thing you can do is actually go, in fact what I might do is restart this with the console. You won't be able to see the console, but at least then I won't get the error messages in my shell here. So the first thing you can do is use FTP to get at this sys, it doesn't have completion, sys tasks. So in mavproxy you can use FTP to download files, but you can also use mavproxy to download these virtual files, and these virtual files all begin with this @sys thing. So there's not actually a file called tasks.txt. It's assembled on the fly on the flight controller to tell you something interesting about what's going on the flight controller. And tasks lists all of the tasks going on in the main thread. Now you can just say FTP get, and then it'll download it as a file and write it to your file system, but that's not terribly helpful because I want to see it as well. So if you put a minus sign on the end here, you say FTP get, and you get a nice long big list of tasks here. Now the other thing to bear in mind is that I certainly for others, I think for tasks, I could be wrong here, but I think for tasks the counters are reset when you do the FTP get. So if you want a sort of consistent picture, you want to do an FTP get, wait for a while, and then do another FTP get. So I've done an FTP get, I've waited for a little while, so let's do another one. Okay, so here we go. So now what you can see is all of the scheduler tasks that are running, and there's some interesting data here. So there's min and max, and these are the min and max times that the task took to run in microseconds. So you can see this update, which is the IMU update function, took a minimum of 26 microseconds, maximum of 84. It gives an average, not terribly useful, but it gives you a little bit about a feel for where most of the tasks are occurring. And then this OVR is overruns. So in the task table, and I can probably just show you this if I switch on VS Code here. So here's VS Code, and if I go to Copter here, so you can see there's a scheduler. This is in copter.cpp, and there's a scheduler table here. So let's have a loop at RC loop. Okay, so RC loop, so scheduler task, this is sort of the canonical way of declaring a task. RC loop says it takes, it runs at 250 Hertz, that's the first number, and then it should take at most 130 microseconds. And this final number is sort of the priority index, so these should be in ascending order. So 130 microseconds. So if we go back to here and have a look, I'll hide VS Code just so you can see now. So let's find RC loop. So we can see RC loop here. There's RC loop, and it says minimum 3, maximum 186. So it actually took a little bit longer than 130, but it didn't think it overrun, which is kind of interesting. I would expect to get some overruns if it was taking longer than the declared time, but that's an investigation for another day. And then the final, so slip means a task slipped, and this essentially a slippage means it couldn't be scheduled in time, and basically slippage will occur on tasks when the processor gets overloaded and the scheduler gets overloaded, and things have to be that other tasks that have taken too long then prevent new tasks from running, and if that goes on for enough, then the task can't be run at all before the next scheduler loop is scheduled to run. So that's what slippage is. And then you've got this total 4.5%, which is the percentage of the main loop, the percentage that the CPU is, or percentage time, so this is actually measured in time, microseconds, percentage that of the main loop the task took to run. And so you can see this. So this percentage is the main number of interest, and you can see that most of these are virtually zero. So these are all tasks that run fairly infrequently and don't take up much CPU. You can see Mavlink taking up a little bit more there. Update dynamic notch taking up a little bit more, 3% there. But and the one I've just looked at, RC loop, is 4.5%, and that's because it's running at 250 Hertz, so it's running quite quickly. But the big offenders here are in this top section. Now, there's something a little bit special about this top section, and although the percentages are correct, these tasks, not all tasks were created equal. So these top tasks with the star next to them, so you can see a little star there, these are what used to be the fast loop. So the fast loop is a part of the scheduler that is always run regardless, and always run to the end regardless. So other tasks, they might get skipped if they've taken too long or they don't need to be run, but the fast loop always runs. So every tick of the main loop, all of these tasks will run in order regardless of how long they took. And if we go back to VS Code and just have a look, you can see that these are declared as fast tasks. So initial sensor update is a fast task, and various others. So these are all what was the fast loop and is now a list of fast tasks. And the reason I did that was so that the individual components could be accounted for in the CPU time costing that goes on in this table. So we can look at all of these tasks. So it's these ones here essentially. Here, all of these, and see how long they took. Now, the interesting ones are this one, read AHRS, which is a little bit cryptic, So 43% of all the task time. Wow, that's enormous. Okay, so that in the main is doing EKF updates. So I'm in Loiter, and so EKF updates are going on, and so that's where most of the time is going on. The second one is this one called Update Flight Mode, 16.6%. So that seems a little interesting. Why does changing the flight mode take 16.6% time? Well, actually, although this is called Update Flight Mode, what it is also doing is running the attitude controllers. So this is where the attitude controller runs, and that's why it takes 16%, 16.5%. So you'd expect the attitude controls, the main control loops of the copter, to take up a decent chunk of time. And so that's where it is. So we've got EKF, attitude, and then some other bits and pieces. Okay, so all right, all well and good. So that all seems good. So how do I tell whether I've got a CPU problem or not? Well, you can't really from here. I mean, you can look at some of the overruns, and if there is actual slippage, that's a really good indication. But overruns could just mean that, and generally do mean that someone's just entered the wrong, put the wrong entry in the task table as to how long the estimate of the task is going to take. So the other key piece here are the threads. So this is all in the main loop, which is a single thread, but the flight controller, Chibios, the operating system that runs, is threaded. And we can look at the threads by doing ftp get at sys threads.txt. Right, so this shows the threads. All right, so I'm going to shut this up. Okay, so here you can see the threads, and we've got a bunch of threads, and you can see the main ArduCopter is the main thread, and then we've got a bunch of other threads. But all you can really tell is how big the stack is and the priority of the thread and what the name is. So that's not a lot of use. So I found this quite frustrating when I was doing some performance investigation. And it turns out that Chibios has a little way of counting the time that each thread takes. It's got a little bit of instrumentation in, and it's a compile time option, so it isn't on by default on ArduPilot, but it is a compile time option. And so what I can do is enable that compile time option. So if I build this, so we're building Maytech H743 PD shot, and then I put -- enable stats on the end. This configures with Chibios stats enabled. Now I have to, because it's in Chibios, I tend to do a clean just to be safe, and then I can do another build and upload. So this is basically the same firmware that I've got currently loaded running, but with this stats feature enabled. Now stats takes a little bit of flash, so it can cause boards that are very tight on flash to overflow, but on this H743 I've got plenty of space, and so it should be easy enough to do. So there we are, building away. It's going fairly quickly thanks to the magic of Ccache, yet another of Andrew Tridgell's many miracles of coding. So Ccache is just a way of not recompiling stuff if all of the source code that you're trying to compile has not changed. So so that's why this is relatively quick. It's still Windows, so all you Linux lovers out there, I'm sure yours goes quicker than this, but it's relatively snappy, which is nice. And of course I built this before, so that's why it's okay. So here we go, nearly there. Of course, fast compiles are, watching compiles is a bit like watching paint dry. So here we go, onto Copter, and should be uploading shortly. There we go, uploading. There we go. You can't hear it because I've turned off the speakers on my computer. There we go, uploading BD shot. Erasing, programming. Programming takes a little bit longer. And done. And then verification is quick. There we go. All right, so that is done. So let us have a look here again. Okay, so here we are, back in loiter mode, and just to show it's the same, I'll get at sys tasks. Now sometimes it takes a little while to initialize, so there we go. Okay, so this task. Okay, so now let's have a look at sys threads. Okay, so here we go, sys threads, and now you can see this all-important load figure on the end. So this is coming out of the Chibios instrumentation, and the same thing applies the first time you do it. It resets the counters, so if you want to get an even sort of statistically significant output, then it's worth doing it once after things have settled down, and then waiting a little bit and then doing it again. So I'm just going to do it again here. Alright, sys threads. Okay, so let's have a look at what's going on here. So to no one's surprise, the biggest use of CPU time is ArduCopter. So the main thread is the biggest use of CPU time. And this is taking about 33% of the total. So this is the total CPU time on the chip. So 33%, about a third. That's quite typical. What you'll find is that if the thing is not overloaded, then all of, like 33% is generally what you'd expect. All of the excess CPU capacity tends to go in this idle thread. So you can see there I've got 7% idle. So it's sort of, I would say I've got 7% CPU free here. ISR is the interrupt service request handler, so it's got 3%. And then we've got some other bits and pieces. So we've got RC out is a little bit big, and that's because it's running BD shot, and that's quite expensive, runs at a fairly fast rate. These times are, apart from the ArduCopter thread, most of these, the CPU time is directly a consequence of how fast, how the loop is running inside the thread. So RC out is running quite quick. I think on this I've got the schedule loop rate set to 800 Hertz, and servo D-shot ESC set to 3, so the output rate is 2.4 kilohertz, so that's running quite quick, which is why we've got this fairly large CPU load. RC in runs quite quick and is quite CPU intensive, so we've got 4% there. And then the other big killers here are SPI1 and SPI4, and these are the two IMUs. So this is a big, so this is like 37% of the CPU is going on servicing the IMUs. And that seems quite large. Yes, it is quite large. But the reason on this copter why it's so large is because I'm running this IMUs at 4 kilohertz. So if I was to reduce it to 2 kilohertz, which is the default, you'd see these almost halve. So 2 kilohertz, these come right down. And at 1 kilohertz, you can go even lower. So you know, if you have a suspicion that you've got a CPU problem, it's most likely that you're running the IMUs too fast. So here I am running at 4 kilohertz, 2 IMUs, and obviously having 2 doubles this up. So I could disable an IMU and get some of that back, but I don't want to do that. So that's where all of the load is going on. And then the other thing to say is to notice is this little star symbol here. And the star symbol is an attempt to indicate that the thread took significantly longer than was expected. Like it basically pegged the CPU for significantly longer than was expected at some point. So there's sort of not more detail than that here, but these generally star is a bit like the equivalent of the overrun flag in the other table. So that's the load. Now you can see that my idle CPU is at 7%. So where is my problem? Where is my CPU problem? Well, there's an additional factor that isn't being considered here, and I'm not armed. And once you arm, logging kicks in. And so this essentially turned out to be my problem. So what I can do is if I set disarm delay to 60, so I don't want it immediately disarming, and then set arming checks to 0, so I'm turning off all of the arming checks. I should now be able to arm the throttle. There we go, you can hear motors armed in the background there. Let's turn off VS Code. And with motors armed, I'm going to do another FTP get. Oh, and I got to. So, okay, so it disarmed because I got this battery failsafe, so I'm just going to arm again. There we go. I'm motors armed, doing CPU threads, and I'm just going to wait a little while. It's you can't see it, but it's basically saying the ESC RPM is too low, so you can't take off, which is kind of fair because there's no battery connected and no ESCs going on. Okay, so let's get the threads. Alright, so now with it armed, now you can see the idle thread has gone down to 0.3%. So that's really marginal. So this copter armed in loiter is basically at the limit of the CPU. It's basically using all of the CPU. And you can see that the IMU usage went up a little bit, and that's partly because there's some of the filtering goes on in the IMU thread. And then you can see the ArduCopter, if you remember, it was 33%, now it's 39%. So that's really where all of my 6% CPU has gone, is in the ArduCopter thread. So the thing to then look at is, okay, so, and here's the bug I was trying to fix. I've just got a radio failsafe. So that's the bug that I was looking at. So this just failsafed on the bench. So if I look at tasks again, okay, so it disarmed, so I'm going to arm the throttle again. Get tasks, wait a little bit. Let's see what's going on. Okay, so here are the tasks, and so what has changed? And if we go up here, you can see this is the thing that is changed. Loop rate logging, taking up 8.4% of the main thread, which is huge actually. That's a huge chunk of time compared to everything else. Okay, so compared to attitude logging. And the other thing to remember here is that, I mean, there's a little bit else going on here, but the most of it is gone in the loop rate logging. And this is not even the logging itself. So the logging itself runs in a back-end thread. So if we have a look at the tasks again. Whoops, not the tasks again. The threads again. You can see there's this log IO thread. So this is the thread that's actually writing data to the log. And you can see that it's actually not that busy at all because most of it's done in DMA. So ironically, the logging is expensive, but most of the cost, it looks like, is actually in the front-end tasks rather than the back-end tasks. So have a look here again. So yeah, so we can see So this will have gone down. Yeah, it's gone down. You can see it's gone down now with disarm to 1.2%. So that's where my time has gone. Now, there's a couple of things I can do here. So one is that if I look at log bitmask, you can see that I've got this bottom bit, 1, set, which means fast attitude. And fast attitude is the one that's expensive. It's basically fast attitude, which logs at the loop rate, plus PIDs, which also log at the loop rate. So this is, I think of that 8%, about 8.5%, 4.5% is in fast attitude, 4% is in PIDs. So one of the things I could do is just turn these off and get back that CPU time. But I don't want to do that because I want to see how the copter is actually performing, especially if I'm in acro. So the other little trick I can do, and this is a little bit naughty, but this is what you can do. Okay, so if we bring back VS Code, all right, so we've got VS Code here, and what I'm going to do is go to the Maytech BD shot HWDEF. So this is the HWDEF, which is the definition file for the firmware I'm compiling. And what I'm going to do, so by default, these run at 400 megahertz, sorry, these chips run at 400 megahertz. And this is because there were some bugs in older silicon, X and Y revs, that meant it couldn't run at a faster frequency. But pretty much no flight controller that ships today has that faster frequency. It has those older revs. And so what you can do is you can add in this little MCU clock rate megahertz here. And I'm setting it to 480, which is the maximum the clock will do. And in theory, this gives me 20% more CPU time. In theory, I mean, obviously there's sort of various optimizations going on, but in terms of raw clock, 480 over 400 should be about 20% better. So I'm setting that. Let's recompile. So, okay, recompile this guy. And load it up again. Unfortunately, I think this changes HWDEF, so it might take a little longer to compile. Yeah, so I'll probably just pause just while we're waiting for that to compile. Okay, so it's now it's finished compiling. It's just doing the programming of the flight controller, which should be done any second now. And there we go. Okay, uploaded. So let's start Mac proxy again. Oops.
No GPS. Stabilized flight mode.
All right, so
GPS 3D fix lock.
let's have a look at this thread. So we'll just wait for things to calm down. GPS is configured. All right, so we'll get the threads, and now that started the clock. So now I'm going to wait just a little bit. Give me so that gives me a
GPS home acquired.
better guess as to what's going on. Okay, so threads. Okay, so here we go. So here's our new thread thing. Now, so a couple of interesting things here. So idle has gone from 7% to 18%. So I've gained 11% CPU. So it's not quite 20% CPU, but it's pretty good. Pretty good. 11% CPU. Well, and of course that's 11% of the current. So it's but yeah, this is much better than I was expecting. And you can see correspondingly the ArduCopter thread has gone down in cost. It was 33% before. Now it's 29%, which is another 12% reduction because everything's just running faster. And you can see the SPI threads are running more quickly here as well, so lower CPU thread. So that's great. So I seem to have better CPU performance. So let's try actually arming it and see what goes on.
Motors armed.
Okay. Oh, it's
Motors
disarmed again. So we'll do this again. Wait a little bit longer. Alright, so here we go, threads. And this time we can see that we have, although the ArduCopter thread has gone up to 35%, I still have 7.5% idle. So I've got bags of room, bags of CPU room there. And and you can see the other things have come down, well, a little bit from, remember SPI1 when I think it was 21%. And there's not a lot of point looking at the tasks because the proportions of the tasks in the main thread should all be the same. It's the CPU time that's changed, and so you can see the ArduCopter time again has come down from about 39% to 35%, and these have come down a little bit. So my little fix to the speed has improved. It's sort of taken me out of that marginal region for CPU. And I put that on, just went out flying, and no fail-safes at all, not one. So all was completely perfect, doing exactly the same conditions as yesterday, same flight pattern, did a couple of batteries, no issues whatsoever. So I'm pretty confident that the issue I was seeing was CPU related, and this is one way to fix it. But of course there are other ways. Use lower gyro rates, don't log so much, and you obviously can turn down some of the other bits and use a lower scheduled loop rate, for instance. That will lower the CPU quite considerably for these tasks that run at the loop rate. So that's a bit of a whistle-stop tour through some of the developer tasks, kind of developer tasks that I did, but hopefully you enjoyed that and found it useful. Thanks for watching.